How many terms are there in each of the sequences? The first sequence starts at 100, goes to 101, 102, 103, and the last term of the sequence is 700. And again, we want to know how many terms there are. So we're going to use the general expression for the nth term. In this case, this is an arithmetic sequence with the first term equal to 100, the nth term being the last term is 700, the common difference is 1. We want to find out what n is, which represents how many terms there are in that sequence. So using the formula for the arithmetic sequence, we know that the nth last term is 700. We know that the first term is 100, plus n minus 1 times the common difference. Now we're going to distribute the 1 to both terms. So we end up with 700 equals 100 plus n minus 1. Now combining like terms, 100 minus 1 is going to give us 99. So 700 is going to equal n plus 99. And then subtracting 99 to both sides gives us 700 minus 99, which gives us 601. And therefore, there are 601 terms in this sequence. Let's take a look at the next sequence. We have 1, 10, 10 squared, 10 to the third power, all the way 10 to the 90th power. So, if you notice here, this is a geometric sequence. And so using the general expression for the nth term of a geometric sequence, with the first term being 1, we know that the last term, a subscript n, is 10 to the 90th power. And the common difference is 10, because 10 divided by 1 is 10. 10 squared divided by 10 is 10. 10 cubed divided by 10 squared is 10. So therefore, we know the common ratio is 10. And again, we want to figure out how many terms there are in this sequence, so we're looking for n. So now we need to look at the form, or the formula for the geometric sequence is a subscript n, which is equal to the first term, times r to the power of n minus 1. So therefore, we put in the last term, which is a subscript n, which is 10 to the 90th, which is equal to the first term 1 times the common ratio of 10 to the power of n minus 1. So if we multiply 1 times 10 to the n minus 1, well then we get 10 to the n minus 1, which is equal to 10 to the 90th. Now, whenever you have the same base, you can have your exponents equal to each other. So now we can say that 90 is equal to n minus 1. Now if we add 1 to both sides, then we get n is equal to 91. And therefore, there are 91 terms in the sequence. In the next example, we have 10,000, 20,000, 30,000, 40,000, all the way up to 100,000. So you can see here that we're dealing with an arithmetic sequence. So we're going to use the general expression for the nth term of an arithmetic sequence, where the first term is 10,000, the last term is 100,000, and the common difference, as you can see here, 20,000 minus 10,000 is 10,000. 30,000 minus 20,000 is 10,000. And again, we're looking for n to find the total numbers of the sequence. So, using our form, we're going to say that the nth last term is 100,000, which is equal to the first term, which is 10,000, plus n minus 1 times the common difference, which is 10,000. So now we're going to distribute this 10,000 to both of those terms. So 10,000 times minus 1 is minus 10,000, and 10,000 times n is plus 10,000 n. Now 10,000 minus 10,000 gives you 0. So therefore what's left is 10,000 n, which is equal to 100,000. So in order to solve for n, we're going to divide both sides by 10,000, and therefore n is going to equal 10. Therefore, we can say that there are 10 terms in the sequence. In the last sequence, we have 1, 4, 16, 64, 256, 1024, all the way to 65,536. So if you notice here, there's no common difference, but there is a common ratio, because 4 divided by 1 is 4. 16 divided by 4 is 4. 64 divided by 16 is 4. 256 divided by 64 is 4 as well. So, using the general expression for the nth term of a geometric sequence, with the first term being 1, and the last nth term is 65,536, where the common ratio is 4, and we're looking for n. So, again, using the geometric sequence formula, plug in our values. So we know 65,536 equals a subscript n. We know the first term is 1 times the common ratio of 4 to the power of n minus 1. Now the next step is the following. Okay, if you notice here, 4 to the 0 power is 1. 4 to the 1 is 1. 4 squared is 16. 4 to the third power is 64. 4 to the fourth power is 256. 4, excuse me, to the sixth power is 1024. And this is actually 4 to the eighth power. So we need to find the same base because 1 times 4 to the n minus 1 is 4 to the n minus 1. So in our previous example, we need to make sure we find the same base. So looking at the number of 65,536, we want to find out where can we find the base of 4? Well, the base is 4. It'll have an exponent of 8, which equals 65,536. Let's just verify that. So if we say 4 to the 8th power, that gives us 65,536. Now, since we have the same base, we can set our exponents equal to each other. And so therefore, 8 is going to equal n minus 1. And now if we add 1 to both sides, n is going to equal 9. Thus, there are 9 terms in the sequence.